All right, we are starting Chapter 10, and in Chapter 10 we're going to start comparing two populations or two groups. So before we've only been working with one sample, but we're going to be starting to work with two. And so in 10.1 we're going to talk about comparing two proportions. So we're kind of taking the same pattern as we have for the last couple chapters. We're going to talk about proportions, and then we're going to talk about the means. So we're going to talk about comparing two proportions today. Make sure you have your green sheets nearby because you're going to need those. And also make sure that you have your calculator because I'll be showing you some stuff in your calculator. All right, so here we go. The learning objectives for this lesson, we are going to learn how to determine whether the conditions for performing inference are met. So again, we're going to have conditions to check. They're going to be extremely similar to what we've already been checking, so that's the good news. We're going to construct and interpret a confidence interval so we can compare two proportions, and you're also going to learn how to do the significance test to compare two proportions in this section. All right, so both of these are important. We kind of did this just in Chapter 8, and then we did this in Chapter 9 within like one sample, but now we're going to learn how to do both of them in one section, and it's on two samples. So I definitely feel like you're able to do it because you should be doing pretty well now with both confidence intervals and significance testing, and so putting them both in there shouldn't be that big of a deal for you. All right, and then the last one is that we're going to interpret the results of our inference procedures in a randomized experiment. So, suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and in population 2. Let's call these parameters of interest P1 and P2. Notice that they're P's and not P hats because they come from a population. So it's population 1 and population 2. The ideal strategy is to take separate random samples from each population and compare the sample proportions with that characteristic. So we're going to take a sample from population 1 and we're going to take a sample from population 2, and then we're going to compare the proportions that we get out of both of them. If we want to compare the effectiveness of a treatment 1 and a treatment 2 in a completely randomized experiment, this time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each experiment. We use the proportions of successes in the two treatment groups to make the comparison. Here's a table that summarizes these two situations. Okay, population 1, here's your parameter, you have your statistic, so your P hat, so it's their sample that came from your population, and then you have your sample size. And then you have population 2, you have P2, P hat 2, and N2. You're going to need to know this notation and probably keep it straight, so knowing which one came from where. So I would probably write something similar to this on my paper when dealing with two proportions, just so that I can keep them straight. And I make sure that this statistic came from this parameter and I don't get them interchanged. All right? And I'm working with the right sample sizes. Remember, it's not necessarily if you can do the actual procedure, it's if you can keep the data going into the right places and you don't make any simple errors. So we need to make sure we're cautious and very tedious almost in our work to make sure that we don't make mistakes. The sampling distribution of difference between two proportions, okay, its shape is approximately normal if n times p is greater than 10 and n times 1 minus p is greater than equal to 10, which is something that we've already done. We know that the center of our shape should be the same as the proportion population, and we already know how to find the standard deviation if the sample is no more than 10% of the population. That's that 10 times little n has to be less than or equal to big N. That's this part right here. We already know all three of these conditions. We've been doing them. 10 times little n has to be less than or equal to big N, right? We've been doing that. We've been checking this. Sometimes you see me write n times q has to be greater than or equal to 10. This we've done for proportions already. This is nothing new. We've been doing it in Chapter 8 and Chapter 9, all the way through as of right now. To explore the sampling distribution of the difference between proportions, let's start with two populations having a known proportion of success. At a school 1, 70% of their students did their homework last night. At school 2, 50% of the students did their homework last night. Suppose the counselor at school 1 takes a simple random sample of 100 students. So as soon as I read that, I know that this right here is my N1. All right? So this right here of their 70% of their students did their homework last night. So I'm going to say this is p hat of 1. That was my, oh no, should be the population, sorry, because they took a simple random sample. So I believe this is going to be my p. All right, and here would be my p of 2, and then the counts are 200 students. That becomes my n2. So you're going to have to be able to pick out this information when you read through the problem. We can say about the difference of P1 minus P2 in the sample proportion. What can we say? Well, if I take P1 minus P2, well, according to my population, 70 minus 20 is going to be greater than 0. Right? So what can we say? We can say that the results should be positive if I'm doing P1 minus P2 if this happens to be correct. That would be what we would expect to see in our sample proportion, would be something similar to what we know about the population from the night before. Right? Using Fathom software, they generated 100 students from School 1 and a separate a simple random sample of 200 students from School 2. The difference in the sample proportions was then calculated and plotted. Okay, so here it is from School 1, here it is from School 2. Notice they checked the conditions for both populations. Approximately normal, because the sample size is large enough. They know that p hat's at 0.7. They found the standard deviation. Then they have to do it again for the second sample. They have to do it twice. Everybody hear me. You're going to have to check these conditions twice. They're the same conditions, you just check it once for this population and once for this population. All right? Okay, so then if the two distributions are already normal, then when we subtract them, they should also be normal. They should be approximately normal. We would expect the center to be 0.2. Okay? And then they get this spread of 0.058. Which is different than these two, and if you look at it, it's not, you didn't just add them. It's 0.058, which is bigger than both of these, but it's not these added together, so they did something here to find the spread. What do you notice about the shape, the center, and the spread of the sampling distribution of p hat minus p hat of 2? Well, the center is at 0.20, which is what we would expect if I subtracted these two. Remember back in Chapter 6 when we had to subtract distributions, probability distributions, and when we did, we could just subtract the means, correct? And so we would do 70 minus 50, which makes my new mean at 20. That would make sense. It's approximately normal because both of them were approximately normal. All right? Now, the spread is what changed, but if you remember, right, from that section, in order to find the new standard deviation, we had to take the standard deviation we had and square it and add it to the standard deviation that we had. So this is of 1 and this is of 2. And then take the square root of it should give me my new combined standard deviation. And remember, this was always addition, even if we were subtracting the two. Remember, even if we were subtracting the two probability distributions, we still added here in the middle. Remember Chapter 6. All right, so that's why this is changing here, and they show you that. Both p hat of 1 and p hat of 2 are random variables. The statistic of p hat of 1 and p hat of 2 is the difference between the two random variables. In Chapter 6, we learned that for any two random variables, x and y, their means, we could just straight subtract them, their standard deviations. Okay, this is the variance. So the variance is just squaring them and adding them. To get the standard deviation, you're going to have to square root that. All right?